Okay, students, so let us start this new topic, which is regarding switching characteristics. Okay, and because till now we had seen the static characteristic regarding these inverters. Okay, and those NMOS based inverters, and we have also seen CMOS inverters. Okay, but now we will see the switching characteristics. These are different from the dynamic characteristic. Uh, in the sense that the dynamic or switching characteristic determines the overall operating speed of digital system. Okay, because if you remember, in static characteristic we did not talk about the timing delays and those things. We did not talk about anything related to the speed, but here uh, we will talk about the delay of the inverters or the circuits, delay of the uh, inverters. Okay, so basically this will help us in determining the speed or the delay of the inverters or the circuits based on these inverters. Okay, and they are also reflecting the transient performance of the devices of the circuits. Okay, and these transient performances are uh, mm, performance are one of the most important design specification. Okay, one of the most important design specifications when a circuit is given to be designed. Okay, when a VLSI circuit is given to be designed. So basically what it is, what we will do here, what we will see here is that how does the circuit behave with respect to time. Okay, or we can say that the behavior of the circuit with respect to time. Okay, so and we will see that with the proper strategy we can actually increase the speed or we can decrease the delay of the circuit. Okay, so what are the things required, what are the strategy, what should be the strategies, and what things should we keep in the mind, in our minds, so that we can work on increasing the efficiency of the circuit in terms of delay. Okay, so basically if you look here in this given diagram. Okay, so we have again the same uh, an inverter, a CMOS inverter. Okay, so this is the first stage CMOS inverter. Okay, and uh, this is the PMOS, and this lower one is the NMOS device. Okay, and okay, again as this is the input given to the gate of PMOS and the gate of the NMOS. Okay, and this is the output taken out from the common point between uh, the PMOS and NMOS. Okay, and this is also the common point where the drain of the PMOS meets with the drain of the NMOS. Okay, so if I can write, this is the gate, this is the source, and this is the drain terminal for the NMOS. Okay, and this is the gate terminal for PMOS. Okay, this is the source terminal for PMOS, and this is the drain terminal for PMOS. Okay, And always remember that when you construct a CMOS inverter, the drain of PMOS should be connected to the drain of NMOS. Okay, and from this common point the output voltage is taken. The output voltage is tapped at the common point between the junctions of two drains of the two MOS devices, here, PMOS and NMOS. Okay, so basically this is the first stage inverter. Okay, and we assume that the output is connected to some next stage circuits. Okay, the output is connected to some next stage circuits, and for the case of simplicity and for analysis, we assume that the output of this inverter is connected to the next stage, which is also an inverter. Okay, so this inverter output is feeding to a next stage inverter input. So basically what it is cascading the inverters in various stages. The first stage inverter is fed to the next stage in second stage inverter, and second stage inverter output is fed to the third stage inverter input, and like that. So you can think of a situation like this. Okay, you can think of a situation like this. Now here, apart from these two devices that we have here, PMOS and NMOS, the most important thing that come here into picture is these capacitances. Okay, so till now we have not considered the effect of capacitances in our static analysis of the circuits. Okay, there we had just tried to describe and analyze the VTC characteristic of the inverter, but here we will see how we can describe how we can define the delay part associated with the inverters. Okay, so we will assume that at the input side we are feeding a pulse signal. Okay, which is nothing but a 0, a 1, a 0, like that. So it's a kind of clock signal, you can think of it like this. Okay, so it is basically a pulse that is switching between 0, 1, 0, 1, 0, 1, like that. Okay, and we know that when input is 0, the output will be 1, and when input is 1, output will be 0. So I can draw for the respective output like this for this given pulse input signal. Okay, so when input is 0, the output will be 1, and when input is 1, the output will be 0, and for the next input 0, output becomes 1 here, right? Okay, so and also I told you that here the capacitances will come into picture. Okay, and these are the one of the most important things to be kept in mind when we analyze the circuit from switching point of view, from its delay point of view. Okay, so we know that this is the gate terminal, this is source, this is drain. Okay, and obviously this is the body terminal, and this is the body terminal or the substrate terminal of the MOS. Okay, so let's start from this PMOS. Okay, and because look at this, the capacitances are present everywhere. Okay, there would be a coupling capacitance, there would be a capacitance present between the gate and source of this PMOS. We call this as CGSP, okay, comma P. So CGS is for the capacitance that is developed between gate and source terminal, and P denotes that it is taken for this PMOS. Okay, and similarly we have a capacitance associated between gate and drain for this PMOS, between gate and drain. Okay, and we have a capacitance between source and body, for this PMOS, between source, this is the source and this is the body. So this is SB, S for source, B for body. Okay, so body means substrate. Okay, it is not taken as S, it is taken as B. Okay, so that it does not get confused with source, because source is denoted by S. and B for body. Okay, and similarly we will have a capacitance between the drain and the body. So this is like this CdB for PMOS. Okay, so we have 4 junctions, and each junction is coupled with another junction with the each terminal is coupled with the next terminal by some sort of capacitance, by some sort of capacitor. Okay, actually there are capacitances present everywhere in the device. Okay, but for our analysis we are representing these capacitances in the diagram. Okay, and similarly when we go for the NMOS device, we will have a capacitance between the gate and drain, CGD, and we'll have a capacitance between gate and source for NMOS, CGSN, and we will have a capacitance between drain and body, CDBN, and between source and body, CSBN. Okay, so these are the capacitances, the 4 capacitances associated with the NMOS. Okay, and the 4 capacitances associated with the PMOS. Okay, so the upper one is PMOS. Okay, the lower one is NMOS, right? And if we can talk about this, that why are these capacitances coming in picture. If you remember, let me draw. If this is the simple architecture, simple for NMOS, remember this is the gate terminal, this is the source, this is the drain. Okay, and this was the body. Okay, so this is gate. Okay. So when I talk about CGD, that is this gate and drain, between gate and drain. Okay, now remember that although we have seen perfectly aligned pictures, but practically they are not, they differ a bit, like let me draw this, the source like this. Okay, and the drain region like this. So what is the difference here? That there is a bit of overlapping between the gate and the source region N plus. Okay, so look at this overlapping. Oh, why this comes? So this overlapping basically I'm talking about. Similarly, there is a bit of overlapping here between gate part and the drain part, that is N plus region for this. This is particularly for NMOS, and for PMOS the materials will change. Okay, so this is basically referring to this CGD GDN. Okay, because this is for NMOS. Okay, so where is CGD? GD is for the capacitance between gate and drain. Okay, so this is the gate terminal and this is the drain terminal. The drain region is this one, and we know that there is a bit of overlapping between gate and drain. Okay, this is the overlapped area. Okay, and we know that this has its own MOS. Okay, metal oxide semiconductor capacitance. Okay, and this is also the metal layer, the oxide layer, and this is again a conducting layer. Okay, conducting layer. So there will be a development of a capacitance due to this overlapped area between gate and drain. Okay, and this particular capacitance is represented as CGD for N MOSFET. Okay, and similarly we will have a capacitance between gate and source for N MOSFET, which will be because of the overlapping area between gate and source like this. Okay, and this will give rise to a small capacitance between the gate and the source terminal for NMOS. Okay, now let us see about how does this CDB and CSB. Okay, So if this is dB between drain and body. Okay, now this is the body part. Okay, the body is p-type material, and this is the drain region. The drain is n plus region. Okay, and this is the junction that is present between the drain and the body. Okay, this is the junction. Okay, and we know that whether the junction is in forward bias or reverse bias, it has its own capacitance associated with it, right? Okay, and we also know that when we operate a MOS device, okay, we tend to keep this junction and also this junction in reverse bias, so that it does not allow any sort of leakage current. The leakage current is kept to minimum between source and the body, and drain and the body part. Okay, so there is a junction here. This is the PN junction. Okay, and similarly this is also the PN junction. Okay, and since these are reverse biased, okay, so the junction, the capacitances arising because of these junctions, we call this as the junction capacitances. So which capacitances are called as junction capacitances? The capacitance between the drain, this is the drain and body, and the capacitance between the source and body, that is this CDBN and CSBN. Okay, so these four capacitances are defined, are clearly available, are clearly seen in the picture, in the device structure. Okay, and similarly we can define the four capacitances associated with the PMOS also. Okay, so just it's a matter of thing that this P substrate will be replaced by N substrate, N plus will become P plus, N plus will become P plus, and we will have the same scenario here. Okay, similarly we can define the four capacitances for PMOS also in the same fashion, right? Okay, okay, and this CG is the oxide capacitance over gate. Okay, this is the thin oxide capacitance over the gate area, and this is present, this is okay, this is connected here. Okay, just look at here, this is V out and this is CINT, and CINT is the interconnect capacitance. Okay, and this is actually the lumped interconnect capacitance. Okay, so this is actually U. Okay, this is lumped LU. The lumped interconnect capacitance. So this is basically the interconnect capacitance that is arising because of the wires or the interconnects that are being fabricated on the circuit. Okay, on the chip. Okay, so all the wires are having some sort of capacitances associated with them. Okay, and every part of the wire is having some small value of capacitance. So it's very difficult to connect capacitance with every point of the interconnect. So to make it simple, what we do is that we connect a single capacitance called as CINT, which is the lumped value, means which is actually the total value of the whole capacitance that is developed because of the interconnects that are fabricated on the chip. Okay, so this CINT is basically because of the wires or the interconnect, and the capacitance arising because of those interconnects. Okay, and this CG is the oxide capacitance over the gate area, because we know that this is the gate area, and we have MOS structure here. Okay, and this is the input of the next stage. So this point will see kind of input capacitance because of this MOS structure here, and this particular capacitance is named as CG. That is the that forms as the input capacitance to the next stage. Okay, and this will be represented at the input side of the next stage or at the output side of the previous stage. Okay, so basically we are having these 1 2 3 4 plus 4 8 plus 1 9 and 10 capacitances. Okay, 4 plus 4 8 capacitances due to the device. Okay, and 1 because of the interconnects or the wire, and the last one, this is because of the next stage input capacitance that comes into picture. Okay, so we will take into account these 10 capacitances when we try to analyze the circuit behavior. Okay.